Is that the reason? Okay, there you go. Maybe human error, but it turned off by itself. You told me that you were hearing me. Okay. Okay. People did not miss anything if they didn't hear online. We're just getting started with some delay. Testing didn't work well. Now, can you hear me online? Hopefully people can raise their hands online and we can do the testing with people online. Okay, nobody says anything, so hopefully they're hearing. If they're not hearing, they'd better be in class, right? I'm just joking because we have other people who are attending that cannot come to class. Okay, yeah. So office hours, some reminders, extra credit assignment, 1, 2. Hopefully you want to get extra credits. Don't let LLMs do that work for you. We can actually see the difference between people who write reviews using LLMs. This happens in the scientific community also. You submit a paper, like original scientific work, and some person reviews the paper, but it turns out that person didn't review the paper because you can tell an LLM reviewed the paper, very likely, or this person was like an LLM. Both of which are not good, in my opinion, in the end, because you get something that's not very interesting, not very deep. You're looking for feedback from an expert that is supposed to give you some really good quality feedback on a paper that you've written, and what you get is some generalized comments that are not very interesting. Okay, that's my, I'm going to start harping on LLMs at this point, but we need better ways of developing these things. Let me finish it that way. Okay, but we're not going to talk about those. We're going to talk about ISAs, instruction set architectures, and I'm going to go through some slides to remind you what we were talking about. We covered the von Neumann machine. I'm going to go through this very quickly again. And we started looking at instruction set architectures, and these are your readings. This was the von Neumann model. You remember the 5 components. We went through all of them. And we said there are also 2 major hallmarks of von Neumann machines, stored program and sequential instruction processing. You should remember this all the time. And we started going through LC3, which is a von Neumann machine. Von Neumann model is an execution model, and ISA, instruction set architecture, implements a version of that execution model, obeying the von Neumann principles. And this picture is a microarchitecture that implements that ISA. And this is one implementation, as I said yesterday, and we were going through some of it. And we started going through some instructions. We specifically covered an operate instruction, add instruction, for example, and a load instruction. Today, we're going to branch out, which is kind of synergistic with control flow, branching out, right? You change the control flow, change the sequence of execution. We're going to see more instructions today, basically. But again, just to remind you, instructions go through a processing cycle, multiple phases of execution: fetch, decode, evaluate address, fetch operands, execute, and store result. And you go back to the fetch to fetch the next instruction. That's the sequential execution, right? You keep doing this over and over for every instruction in the program until you get to the end. And we discussed that we have a stored program computer, meaning you don't distinguish between instructions and data. Whether a value fetched from memory is interpreted as an instruction depends on when that value is fetched in the instruction processing cycle. I said this yesterday, but I didn't put it into words. Now it's put into words on the slide also. So for example, when you're fetching from memory, and if you're in the fetch cycle of the finite state machine, you have seen, you interpret that memory value as an instruction. At that point, whatever you fetch from memory is interpreted as an instruction and put it into the instruction register, if you remember, IR. But if you're in the fetch operand stage in the finite state machine, in the instruction processing cycle, and you're doing a fetch from memory, then you interpret the memory value as data. Right? So it could be exactly the same memory location. The memory address you generate and put it into the memory address register could be exactly the same in the fetch state and the fetch operand state, except how you interpret it depends on whether you're doing it at the fetch stage or the fetch operand stage. Okay. And this was the last thing, one of the last slides we covered. Not the last one's going to be the next one. We were actually going into the control flow instructions that change the sequence of execution so that you can do hopefully more meaningful things like decision making in your programs. So this is an unconditional branch or jump. You can see that this operates on base register. So this is the encoding. We went through some encodings also yesterday. This is the opcode. And this is the base register. The rest are set to zeros, meaning that they don't They don't matter for the purpose of this instruction. And the semantics of this instruction is change the program counter or update the program counter with the value that's stored in register 2, right? Base register in this case. So this is called register addressing mode. We're going to see addressing modes later today. But this is an example of a jump, right? And there are other examples of jumps that we will not necessarily see, but we may look at later in lectures. So how does this work? If you want to implement this in microarchitecture, you need to provide the data path or path from the register file, take one register and place it into the program counter. And that's what we do basically. You access the register file, get the source register 1 out. And how do you know it's source register 1? You basically index one of the source registers with bits coming from the instruction register over here. And you know exactly which bits over here, these 3 bits. And once the data is out, you ensure that in the execute stage of this instruction, the program counter is loaded, meaning you write enable the program counter such that the data flowing from source register 1 goes into the program counter. Make sense? And you should know essentially the logic that goes into all of this, because we have actually developed the registers, wires, and you know how a register file is accessed also. You're going to see more and more of this later on. Does that sound good? Okay, so that's a jump. Okay, so this is the slide that we stopped at actually. I will maybe go through this relatively quickly. But this is the state machine or part of the state machine that we looked at. It's not exactly the same state machine because this is a more instructional version. But essentially, this is what you do during fetch. You have state 1. Every instruction goes through these 3 states. In the first state, you load the memory address register with the program counter. And for this to work, the sequential logic should assert gate PC and LDMAR. If you remember the gate PC, this is the gate PC over here. This is you take the value in the program counter. This tri-state buffer is enabled so that the value in the program counter gets loaded on the processor bus. It's flowing, and you ensure that it goes to a memory address register. We went through this yesterday. I'm going through this again just to remind you. But to make sure this happens, you need to also write enable the MAR in this state, meaning LDMAR signal is asserted. Okay, so the key takeaway over here is you have a finite state machine that's controlling the execution of every instruction in the machine, and every instruction in this case goes through a state 1, 2, 3. And in state 1, you have some control signals asserted. In this case, the control signals are gate PC and LDMAR, such that the program counter gets put into the memory address register. And then you also update the program counter by incrementing the program counter by 1. This is LC3. It's word addressable. Every instruction is a single word. So you go to the next word. So there's something else that's asserted. If we go back to that over here, switching between these two are too much overhead. But essentially what we do over here is in the fetch state, you basically take program counter, increment it by 1, and you need to have data path elements to enable that. And the PC mux, this multiplexer, should select this input, and load PC should be asserted so that you actually increment the program counter by 1. And the reason why we increment program counter by 1 is because we're kind of done with this instruction, right? Done in the sense that we fetched it. We're going to write the instruction to the instruction register. We didn't fetch it completely yet. We're going to fetch it actually in state 3. But we're done with the program counter. We actually took the program counter, put it into the memory address register, and we are going to fetch from that address. Now we should move on to the next instruction. So this is a design choice that someone micro-architecting the machine made. You could have incremented the program counter somewhere else, essentially, right? It didn't have to be done in this state necessarily, right? As long as you did it before you start the next instruction. And you don't start the next instruction until you finish this particular instruction that's pointed to by the PC. Okay, so I'll go through the remaining states a little bit more quickly. The next state is memory access state. Basically, you wait until the memory returns the data in the MDR. So you need to make sure that load MDR signal is asserted. But this is just instructive because it doesn't have an arrow over here that should be going. This is a conditional. It's a state where you stay conditionally. If the memory is not ready, you keep staying in the state until the memory becomes ready. Okay? You will see the full picture in the next slide. And then when the memory is ready, the data is in the MDR, and you need to ensure in state 3 the finite state machine makes sure that the data in the MDR gets put into the instruction register. Let's go back to that over here. So in this picture, assume that the memory is finished and loaded the data into the MDR. We need to make sure that data flows from MDR into the IR, instruction register. To be able to do that, the control signal for this gate MDR should be asserted such that this tri-state buffer is enabled. The data from MDR flows onto the wire, and then after it flows onto the wire, it's flowing here. And we need to capture it in the instruction register such that, and to be able to do that, we need to write enable the instruction register. So LDIR signal is also asserted. Okay? So it's very simple, basically. Of course, as a microarchitect, we'll need to design this finite state machine, but here someone designed the finite state machine and gave it to us. Okay, this next state is decode. In this decode state, basically what happens is the finite state machine checks the opcode, which is the top 4 bits in the LC3 ISA, top 4 bits in the IR instruction register. And based on that, it decides which next state to jump to. And this next state, the term is based on the opcode. For example, if it's an add instruction, if it's an add opcode, you go and follow the sequence of these states. If it's a load register opcode, you go and follow these states. If it's jump, like what we have seen, you go and follow these states. So in case of jump, you go to a state where in that particular state, let's say, the register ID that we have seen earlier gets loaded into the program counter, which is essentially what we have shown in the previous slide. This is state 63. In state 63, you ensure that the control signals are such that PC is loaded again, and you actually access the register file using SR1, which is coming from the instruction register over here. Okay, so hopefully this is clear. If not, you can study it a little bit more. There's no magic involved. This is all based on everything that we have learned in the digital design part of the course, and now a little bit microarchitecture part of the course. It's a finite state machine. And the full state diagram is here, essentially. This is actually the real diagram. The previous one was kind of like a toy diagram to illustrate the decode phase. You don't really need this particular state, actually. You can jump directly into a state where you update the PC with register, as I will show you right now. So these are the 3 fetch states. This is the decode phase. And then if this is a jump, if you can read the jump over here, that's a jump. You directly go to, in this case, state 12. And you load the program counter with the base register. And the next state is 18, where you do the fetch for the next instruction. And this is LC3B. LC3B is byte addressable, so you increment the PC by 2. So these are all things that you need to think about for different ISAs, instruction set architectures. Make sense? But principles are the same. You can build a state machine like this for MIPS. You can build a state machine like this for x86 or this computer over here, except the states will be a lot in that particular computer. Okay? Okay, so that was the instruction cycle. Now let's go into instruction set architectures a little bit. Any questions before that? This all makes sense, hopefully. Okay, so we're going to go a little bit more. I mean, we have been talking about instruction set architectures, but we're going to talk about a little bit more other things like data types, addressing modes, and a little bit more on opcodes before that. And we have clearly studied add and LDR in a little bit more detail, even though you may not have realized that I actually gave examples from add and load register. And these are actually using opcodes. Clear there are opcodes over here. They're using some addressing modes, which we called out, but we're going to see more addressing modes. And they're also using some data types. For example, this add is operating on 2's complement integers, which you may have read about in your book. I'm going to briefly mention that also. That's the only data type in LC3. But they could be operating on floating point data types also. And we're going to have some fun with data types also. Okay, so what is instruction set architecture? Essentially, it's really the interface between what the software commands and what the hardware carries out. So you saw a version of this in a previous lecture. This is a simplified version. You have written a program, and you have a microarchitecture. Instruction set architecture is really the interface between the software program and hardware microarchitecture. I'm going to loosen this later on a little bit, but this is actually the hard definition of the ISA. It specifies many things. As you will see, it's actually more than that, but at the basic level, it specifies a memory organization, which we have seen. It specifies the address space, addressability, whether you're word or byte addressable, for example, and we've seen examples of this. It specifies how many registers you have near the ALUs. In LC3, it's 8. In MIPS, it's 32. And we've seen that also. And then it specifies the set of instructions. And the set of instructions are defined by multiple things: opcodes, data types, and addressing modes. And also on top of this, length and format and encoding of instructions. And you've seen all of these in some way. Now let's talk a little bit more about them. Okay, opcodes. So essentially, there are a lot of trade-offs that you can make when you actually design an ISA. How many instructions do I have, for example? Do I give thousands or millions of instructions, or do I have only a basic set, maybe 10, 12? This is actually an interesting trade-off, and we're going to cover the trade-off a little bit. But it could be a large set of opcodes or a small set of opcodes. Clearly, if you have a very large set of opcodes, this complicates the hardware design, right? The hardware needs to support 1 million different instructions. If you have only 10, the hardware needs to support only 10, right? The hardware can be simpler if the number of opcodes is smaller. This is actually the thinking behind reduced instruction set computers. So MIPS, for example, the ISA that you're going to use in your labs, and the ISA we're following is really a reduced instruction set computer with fewer opcodes. Okay, for example, this is an opcode that was there in Hewlett-Packard's precision architecture. You can see that A times B plus C. It's multiply and accumulate, which may not be a bad idea. You put together two things, right? As opposed to just having a multiply and separately having an add. They decided, in addition to having those separate things, also let's have a multiply and add, right? And you could make it a floating point multiply and add, which makes it nicer for machine learning workloads of today. Later in lectures, when we talk about SIMD and GPUs, we'll also talk about multimedia extensions. These are instructions that operate on many data values at the same time, concurrently. We're going to talk about them. You may have heard, for example, streaming SIMD extensions, advanced vector extensions, and more recently, advanced matrix extensions. These are opcodes that are actually operating on many data at the same time, which could be useful for matrix operations, for example. There could be very complicated opcodes, like VAX ISA had an opcode to save all information of one program prior to switching to another program, all of the registers and some of the special purpose registers. So you can imagine many things over here. The sky's the limit in the end. And if you define it in the ISA, then somebody needs to implement it in hardware. So there are many trade-offs involved. Hardware complexity versus software complexity. Some of these opcodes make the software simpler in the sense that at the high-level language, you have some constructs, right? It could be nicely matrix multiplication. So if you're doing matrix multiplication, and if you have an opcode that says matrix multiply, that's a very nice fit, right? You don't need to translate it with a lot of effort. If you have an opcode that is, if your opcodes are not, if your instructions are not that high level, if they're just, for example, add and shift, then you need to translate all of those matrix multiplication operations to adds and shifts, right? And that's a lot of work for someone. It could be the programmer, it could be the compiler, but someone needs to complicate their lives. So software complexity increases if your opcodes are not matching the high-level language. There are also trade-offs like if you have simple instructions, simple opcodes, latency is shorter. If you have complex instructions, they can be they may take a long time. We'll learn more about that later on. So there are interesting trade-offs. I'm going to get to this in a little bit more. So in LC3 and MIPS, there are 3 types of opcodes, and we have seen them actually: operate, data movement, and control. And we're going to see some examples. This is all of the opcodes in LC3. LC3 is a really simple educational machine. You can see the instructions over here. We're not going to go through all of them. If you're interested in them, you can read the book. But this is the opcode, basically. Top 4 bits is always the opcode. So this is very easy to decode. You basically look at top 4 bits, and you know what you're going to do in the instruction. I mean, there are also extended opcodes, as we will see a little bit. So there's this bit over here that kind of enables you to interpret some part of the instruction. This could have been part of the opcode, but they decided not to put it as part of the opcode. So there are some bits over here that also determine what the instruction should do, in addition to the opcode. Okay, this is LC3B, and they changed it a little bit. This is byte addressable. And instead of having a NOT, they have an XOR. And by now, we should probably figure out, know how to implement NOT using an XOR. I'll let you think about it. I'm going to ask that question later again. So you don't need a NOT operation. If you have NOT is unary, right? Basically, that's a single operand. If you want to take the bitwise NOT of something, you could actually do it using a binary operator like XOR. And you can think about it. And there are some opcodes that are not used. In the future, they may extend it, for example, right? You may actually say, oh, okay, a lot of programs may need this opcode, so I'm going to, in the future incarnation of the ISA, I'm going to map that to something else. Okay, so these are the MIPS instruction types. It's actually a little bit more complicated. There are 3 types of instructions in MIPS: R-type, I-type, and J-type. And we've seen all of those in yesterday's lecture. We looked a lot into R-type, for example. R-type opcode is 0. But the real opcode for I-type is really in the funct part, this function. I-type, basically R-type operations are register-to-register operations. You have 2 register operands, 1 destination register, and the opcode and function together determine what you do to the registers. Right? I-type is the source. You have a source register, and then you have an immediate value, and you do an operation on those, and the opcode determines what that operation is. And there's also J-type. This is jump, essentially, as you have seen. You have an opcode and then immediate. Using this huge immediate value, you decide where to jump, for example. Okay, so let's take a look at this R-type instructions a little bit. This is from your book. You can see that opcode 0 is 0 in these R-type instructions. And once you see that opcode is 0, the decoder needs to look at the bottom 6 bits, which are funct. Essentially, that defines the operation. For example, if the funct is 0, you do shift left logical. If the funct is this 26, you do a divide operation. Right? And you can see there are many operations over here. There are adds, there are subtracts, there's NOR, there's XOR. So this is what they decided. Again, somebody decided that these should be the opcodes, and those are the ISA designers when they design MIPS. Make sense? And you can see that these opcodes are not that complicated. Right? These are actually relatively simple. You don't see a matrix multiply here. In later incarnations of MIPS, people may add them, but they're not here in this incarnation. Okay, so those are opcodes. Let's talk about data types now. So an ISA supports 1 or several data types. Basically, this is how you interpret the data. The data you access in the register file, and you want to do an add operation. How do you interpret that data value? Is it a signed value? Is it an unsigned value? Is it a 2's complement value? Is it a floating point value? Basically, in LC3, the designers made the decision that it's all 2's complement integers. Right? Essentially, what is a 2's complement integer? It's a system, arithmetic system, where the negative of a binary value x is defined to be the bitwise not of x plus 1. And this makes the nice thing that if you actually add x and the negative x, you get a 0. In some other systems, you don't get that in some arithmetic system. So it's an arithmetic system. Again, we're not going into computer arithmetic that much in this course, but there is a huge design space of how you do arithmetic using computers. And this is one very commonly used way of doing arithmetic. The negative of a binary value x is the bitwise not of x plus 1. Okay, and if you're interested in this, you can read H&H chapter which talks about 2's complement. MIPS, in addition, supports other things, like 2's complement integers, yes, but also unsigned integers, meaning integers treated as unsigned. It's not signed, everything is positive, or you can think everything is negative, right? That's another way of thinking. Or it has floating point arithmetic also. So there are trade-offs involved over here. Again, hardware complexity versus software complexity. If you actually have lots of data types, hardware becomes more complex. But software may be easier because in software, you may have actually different types of things. For example, you may actually have a matrix as a data type, right? None of these are supporting matrices, but some of the advanced matrix extensions that are incorporated into general purpose machines today are supporting matrices because of the importance of machine learning. Okay, and again, there are trade-offs in terms of latency. If you, for example, have a supported data type, latency is fast. But if you don't have a supported data type, for example, again, as I discussed earlier, if you want to do a matrix multiplication, but matrix is not supported as a data type, what is supported is only unsigned integers, let's say, you have to convert every operation that you do. You have to convert a full matrix multiplication to many operations on unsigned integers. Okay, now let me give you the high-level perspective, and then we're going to go into a little bit more detail. This course is about hardware-software interface, right? We are going to talk a lot about that later on, especially when we go into other execution models. But this having different data types in the ISA is a very good example of the trade-off that people make between hardware and software. In other words, programmer and microarchitect. Programmer is who implements software, microarchitect is who implements hardware. If you have more data types, this is good for the programmer in general. If you have fewer data types, this is good for the hardware designer in general. So why? Because if you have more data types, it enables better mapping of high-level programming constructs to the hardware. Hardware can directly operate on data types present in programming languages, for example. This way, you get small number of instructions and a smaller code size. Your programs in assembly will be compact in machine code. So they can fit small memories, for example, right? So I've already given you examples from matrices, right? You can have matrix operations. A single instruction can say multiply matrix A and B, store the result in matrix C. And of course, there's a description of what these are exactly. But one instruction can unleash huge amounts of work on matrices that could be very large. As opposed to, you only have multiply, add, and load and store instructions like we're going to have in MIPS and LC3. And you convert the matrix operations into those smaller pieces of operations. Then you have lots of instructions, right? As opposed to having a single instruction that does all the work, you may have millions of instructions that do a matrix multiplication. Think about that. There are energy consequences of this also. Another example could be graph operations. If you're operating graphs on graphs, for example, you do a graph traversal, for example, and you may have graph traversal operations in the ISA as opposed to individual load, store, add instructions. Again, you can have much better code size and also much better mapping of high-level programming constructs to hardware. The disadvantage of these complex data types or more data types is much more work for the microarchitect. Now, the hardware designer, microarchitect, needs to implement the data types and the instructions that operate on the data types. So once you have data types, you also need to add instructions that operate on the data types, right? Matrix add, matrix multiply, matrix transport, transpose. All of those are operations. Yes?
Wouldn't it also be possible to implement certain operations on hardware and make it fast?
I mean, you can make all of these fast, right? You can make a single add fast, move fast. But yes, you can make the matrix multiply fast also. So if you have an instruction, then the hardware designer can customize it. Yes, exactly. So that's another benefit of more data types, certainly. But it's still more work for the microarchitect. That's the disadvantage. It enables better mapping, and you can customize it. You can reduce the latency, but it's more work. Make sense? Okay. So another way of looking at it is a semantic level, right? If you think about data types, they're really tightly coupled to the semantic level or complexity of the instruction. I'm going to introduce a concept of semantic gap, which is a good way of thinking about instructions that architecture design. Essentially, semantic gap means how close are your instructions and data types to the high-level language. Pick your favorite high-level language, Java, Python, C. C is still high-level, even though it's relatively low-level. Rust. If you're closer to the constructs in that high-level language, then you have a low semantic gap. So if you have complex instructions and complex data types, you have a small semantic gap. If you have simple instructions and simple data types, you have a large one. So let me give you a few more examples. For example, you can have an instruction that inserts into a doubly linked list. This makes your life easier, right? A hash map instruction, right? An instruction operates on hash maps, or instructions that operate on key value stores. VaxISA actually had some of these. You actually had a low semantic gap, small semantic gap. You had instructions that operate on doubly linked lists. You had instructions that operate on multi-dimensional arrays. Today, we have matrix operations, which are similar to what we had a long time ago with VAX, for example. And they cater to these heavily used workloads that work on matrix operations, right? Simple instructions we've already seen, right? Basically, you have primitive operations, load, store, multiply, add, NOR. And essentially, early RISC machines, reduced instruction set machines, had only integer data type, for example. Later, they figured out this is not good enough, so we're going to add more data types. So if you're too simple, you quickly figure out that this is not enough, because there's a huge software world out there, and you didn't really support the software nicely. Your semantic gap is too far from the high-level language. As a result, you figure out and you keep adding to the ISA. If you're too close to the software, then your operations may be at some point not so useful, especially if the software world evolves and start using something else, right? So your ISA also may get outdated. So it's good to think about this a little bit. Okay, so let me illustrate this a little bit pictorially. essentially we're talking about how close instructions and data types are to high-level language. You have a high-level language, pick your favorite one again, and then you have control signals at the low level. In the end, your goal is to map the high-level language to the control signals, of course, over many clock cycles, right? If you set your instruction set architecture close to the high-level language, you have a small semantic gap, right? You're far away from the control signals. A matrix multiply is much farther away from a control signals than a NOT or AND or an OR operation, right? If you have an instruction set architecture that's with simple instructions and simple data types or few data types, you're closer to the control signals. So you have a large semantic gap. Now you see the complexity now, right? Now this mapping is hopefully easier for the software, harder for the hardware designer. Again, hardware designer, as your fellow student said, can optimize things. They can still make whatever instructions that are defined over here as fast as possible, but they still need to do the work to do that. If you're here, then the hardware designer's job is easier because you're closer to hardware. Now the software designer's job is harder, perhaps, right? Because they need to get high performance using very simple operations, right? Okay, so let me wrap it up. You see the similar pictures with addressing modes also. So we're going to add addressing modes. But usually people talk about complex instructions and simple instructions, right? Complex data types and simple data types. A good definition of complex instruction is an instruction that does a lot of work. Many operations, basically. And we've talked about some of these, right? You could, for example, have an instruction that copies one string to another. Or you could do that operation using loads and stores only. You could do fast Fourier transform, for example. Right? Simple instructions, an instruction does little work, but it's a primitive using which complex operation can be built. Add, XOR, multiply. So the advantage of complex instructions and data types is you have much denser encoding. Your programs are much smaller. You have smaller code size, which means that you don't need a lot of memory, hopefully, at least for the code. You don't need to fetch that program far away from memory and storage into your on-chip caches, as we will discuss later on. And because everything is smaller, you keep things on chip. So we're going to talk about caches. This is good for caching, for example, as we will see later on. Also, you have a simpler compiler. No need to optimize small instructions as much. And maybe you have a simpler person who is writing programs, right? Because you can map the high-level language to the ISA more easily. But of course, this comes with disadvantages as well. You get larger chunks of work. And as a result, the compiler has less opportunity to optimize with complex instructions. But if you also provide the fine-grained instructions like NOT, XOR, multiply, etc., maybe the compiler can choose the best of both worlds. Now the compiler is not as simple anymore, though. Okay, and clearly you get more complex hardware because you need to translate from a high level to control signals, and the optimization needs to be done by hardware. Okay, so this is a summary essentially. Does this make sense? I didn't go into like how to optimize, etc., because that's the subject of a later. Some of the later lectures, but you can also take a compiler's course if you're interested. Yes?
But isn't a huge disadvantage that wasn't listed that basically if you have multiple really complex instructions, that's like the throughput is going to be really bad. But you won't use them all the time, whereas if you have fewer instructions, they will have a huge throughput, so you can kind of dedicate more space on the chip to those that are useful.
I mean, not necessarily. You can do very similar optimizations for large instructions also, right? That's performance optimization. That's the reason why I didn't get into performance optimization here. You can optimize the performance of a chip whether or not you're having complex instructions or simpler instructions. If you have lots of complex instructions, yes, you need more area, perhaps, to support them. But as we will see, you can change the trade-offs also. So we will see some ways of changing the trade-offs. Depends on the workloads you're executing. Yes, certainly primitive instructions, you can map everything to them, right? But yes, if you have more specialized instructions, clearly they're going to be used fewer times. I agree. But depends on the workloads you're targeting also, right? Clearly people are adding these complex instructions today because some of the workloads are so important that you don't, and you can optimize those operations because there are benefits to it. So in the end, when you're actually doing the performance optimization, you need to think about what workload you're optimizing for. and you need to optimize for the common case. Okay? Okay. Okay, let me give you an example. This is a fun example that I use. This is a data type, binary coded decimal. Do people know what this data type is? It's not covered in your books, I think. It is supported by the x86 ISA. It is covered in your books? Maybe, maybe not, okay. Basically, you encode each decimal digit with a fixed number of bits. So this is how I would represent time. 10, 37, 49. And by now, you should be able to read this, right? I hope. This is 10, right? Essentially, to represent the first digit, you need two things. And this is the least significant bit. To represent the second one, you need 4 bits. Think about why. Because there are 10 different values this can take, right? And 4, it gives you 16. So you encode this with a binary, 4-bit binary value. This is 37, 1, 2 over here. So you need 3 bits over here. And 7, 1, 2, 4, 7. Now, hopefully you got the idea. And this is 49. You need 3 bits again here, 1, 2, 4. And now to encode 9, you have 8 plus 1. Now, if your brain was wired to process this data type, you wouldn't have to go through this exercise. You would just look at this and say, this is 10, 37, 49. But your brain is better wired, either by nature or nurture, to read that, right? So essentially, maybe our computers are not using this data type natively. It is a data type, though. People use it. Which clock do you prefer? Now, if you were always using from your birth this one, maybe you would prefer that one. This is good to think about. Don't say I prefer the left one because I'm a human. Maybe some other humans would prefer that one if they were using that one from birth and they never saw that one. Okay, good to think about. Okay, that's data types. And I think that's a great example of a data types. Okay, addressing modes. This will make things a little bit more complicated. Essentially, addressing mode is a mechanism for specifying where an operand is located. We discussed this already. In LC3, there are actually more addressing modes than in MIPS. LC3 makes a different trade-offs in this case. It's more complex. There's an immediate or literal mode. The operand is in some bits of the instruction, and we've seen this. We're going to see more of this. There's a register mode that we've been seeing. The operand is in one of the general purpose registers. And there are 3 memory addressing modes, which we're going to see. We haven't seen some of these. We saw base plus offset. We saw PC relative, actually. We didn't see indirect, which is an interesting mode, but we were going to see that. MIPS actually has pseudo-direct addressing, but doesn't have indirect addressing. It has base plus offset also. It has immediate as well. So there are quite a few of these addressing modes, but it doesn't have indirect, for example. Okay, why do we have different addressing modes? Again, the same trade-off. I'll go through this relatively quickly. This is another example. If you have more addressing modes, you can map the high-level programming constructs to hardware better, because some accesses are better expressed with a different mode. You get reduced number of instructions and code size. For example, if you're indexing arrays, especially multidimensional arrays, you may have an addressing mode that makes it easier. You can have indirect addressing modes that make pointer-based accesses easier. You can have an addressing mode, for example, if you have matrix operations, again, if you want to access one element in the matrix, you can specify x, y coordinates. And if your matrix is multidimensional, for example, x, y, z, t, p coordinates, if you can think multidimensionally, of course, that make things easier, right? And if your matrix is sparse, meaning you have a huge matrix, but most of the values are zeros, maybe you have a different addressing mode to encode where those zeros are, and your hardware can natively support those addressing modes. Okay, so clearly you can imagine many things, and you will dedicate hardware for these, so that needs to be there. This is a disadvantage, again, if you have actually more of these addressing modes, there's more work for the microarchitect, and also maybe more options for the compiler to decide what to use. So here, the compiler actually may become a little bit more complicated as well, if you have too many options. Okay, so this is a semantic gap. I will not talk about this again, but you can, essentially what I've done over here is to add addressing modes also. So your semantic gap depends on what are your instructions, what are your data types, and what are your addressing modes. Okay, there are many other trade-offs in ISA design, which we're not going to talk about right now, at least. I'm going to talk about instruction types and addressing mode types. So let's jump into operate instructions a little bit more. So in LC3, there are 3 operate instructions. Not we discussed. It's a unary operation, one source operand. It executes bitwise NOT. There's add and end. They're binary operations, two source operands. And we said that the data type is 2's complement. And end is bitwise, actually, SR1 and SR2. In MIPS, there are many more. There are many R-type instructions that I've shown you earlier. I don't want to talk about everything, of course. There are I-type instructions, meaning there are versions of this with one immediate operand and one register operand. And there's F-type operations, which are floating point operations. And again, I'm going through this relatively quickly because we've seen examples of this, and these are not difficult concepts. But let's take a look at one example. This is NOT in LC3. You basically take the NOT of R5, store the value in R3. And again, we've gone through this exercise, a similar exercise. You can figure this out easily by looking at a manual, LC3 manual, which is your book. And NOT is an easy operation. You take the value in the source register, bring it to the ALU. ALU performs bitwise NOT, and you get that from the finite state machine, meaning the decoded instruction. Instruction registers decoded version specifies that this is a NOT, and generates a control signal saying ALU should perform a bitwise NOT. And you get the bitwise NOT of the source register into the destination register. So this is all done in microarchitecture using control signals. So there's no NOT in MIPS. How is it implemented? Again, maybe I should not, yes. Yes, exactly. XOR with one, that's one way of implementing it. Another way of implementing it is using NOR. Now you can think about that also. That's a good, basically. You could do it multiple ways in MIPS, actually. So you don't need a NOT in MIPS. That's the reason they don't have a NOT in MIPS. And that's the reason they removed NOT in LC3B also. LC3B replaces NOT with an XOR. They don't have a NOR either. But again, I think you answered both of the questions over here. But you could do a similar thing with NOR. Okay. So operate instruction. We're already familiar with add and end with register mode and R-type in MIPS. Now let's see how we can do things with immediate operands, right? We'll use subtraction as an example because there's some instructive value to subtraction, especially with 2's complement values. Let's take a look at how subtraction is implemented in LC3 and MIPS. So recall, we have seen this already. This is register to register operation. And if the opcode is add, this is in LC3. If the opcode is 0001, you add source register 1 to source register 2 and store the result in destination register. If it's AND, you do bitwise AND between source register 1 and source register 2. Okay, you've seen this before yesterday. Now let's take a look at how this is done with immediates. Now you make use of this bit over here, bit 5 over here. It's called a steering bit. Let me finish this and we'll take a break. So bit 5 is a steering bit. Here you see that these are all set to 0. Bit 5 is the important one over here. Now, if the opcode is the same op as the register mode at 0001, but if this bit is 1, you interpret the lower 5 bits as an immediate, as some literal value that's encoded inside the instruction. You don't go to a register. So essentially what you do is you take source register 1, value in source register 1, add to it, because the opcode is add, this immediate 5 bits, sign extended. Sign extended mean if you have a 2's complement value, that's 5 bits. The top bit tells you whether it's negative or positive, right? If it's 0, it's positive. It's 1, if it's negative. Sign extension means that take the top bit, replicate it for the remaining 11 bits. Okay? That gives you the full 16-bit value. Okay, so that's the idea over here. If the opcode is AND, which is 0101, you take the source register and you do a bitwise AND with that and the sign extended immediate 5 value from here. Okay, I think we've already discussed. So the key is basically the same opcode is used, but this is an extension of the opcode. This is also called a steering bit. In your book actually talks about it as a steering bit. It's also it's really an extension of the opcode. By just looking at this, you don't exactly know what to do. You also need to look at this, right? Does that make sense? So when you're decoding an instruction, this 1512 gives you some information, but not the full information about what you will need to do. It's an encoding issue. So let me finish this and then we'll take a break. Essentially, this is the encoding. You can write an assembly like this. You can see that I can express a negative value because it's a 2's complement 5-bit value over here. You can easily express a -2 over here. It looks like this. This is the negative value, immediate 5. You can convince yourself that that's -2. In two's complement arithmetic, that is -2. And this is what will happen in the hardware. Essentially, the source register is R4 in this case, so you get the value in R4. It goes into one input of the ALU. The other input of the ALU is selected from either the register file or the instruction register, which contains the bottom 5 bits that we want. And we have a sign extension logic that replicates the first bit, makes it a 16-bit value, and then you have a multiplexer. And let's guess what this multiplexer is controlled by. It's bit 5 from the instruction register. Basically, bit 5 says, if bit 5 is 0, take the value from the register file. If bit 5 is 1, take the value from this data path element, which is sign extended last 5 bits of the instruction register. And this way, you can implement a full add. Depending on whether bit 5 is 1 or 0, this still executes the right thing. If bit 5 is 1, you get the sign extend immediate. If bit 5 is 0, you get the register. Hopefully that makes sense. Okay, so this is where it sits in the data path. And this is where you see the bit 5 over here. Okay, I think this is a good place to stop. I'm going to show you an example of how to do this in MIPS, and then we're going to look at the trade-offs in terms of subtract and add. Let's be back when the bell rings, and we're going to continue with this. Okay, you can hear me hopefully, right? Okay, so remember that we were talking about instructions, operate instructions with literals or immediate values encoded inside the instruction. So one of the reasons, or a major reason why this is provided in instruction set architectures is to make sure you don't waste a register. So if you know that you're decrementing or incrementing, for example, by a register by some amount, you can encode that information inside the instruction itself, right? That way you don't waste a general purpose register to store a +1 or -1, right? So it's good to think about the trade-offs. In fact, x86 ISA has an increment instruction. It's basically a very specialized instruction that does increments, right? So this is not an increment instruction. It's a more general purpose instruction because you have 5 bits of immediate that you can use to do more than increment. You can add any 5-bit value in 2's complement, but you save a register essentially that way. But of course, if you need to add a known value that's larger than that can be represented with 5 bits, then you need to store that in a register, and then you do a register to register add. You cannot use an immediate. So that's the trade-off with literal and immediate addressing modes. Okay, we've seen how this works, and we have seen that we're complicating the data path so that we can actually execute this instruction. It's not that bad, but it's complicating the data path still. Now let's take a look at a similar instruction, MIPS. These are I-type MIPS instructions. They actually have different opcodes than R-type. You essentially have 2 register operands and immediate. Some operate and data movement instructions are like this. It looks like this essentially. In MIPS, instructions are longer, as you know. Opcode is 6 bits, and you have an immediate that's 16 bits. Okay, opcode is operation, RS is source register. RT could be the destination register in some instructions, like add or load, add immediate or load word. It could be source register in others. So now it's not actually very clean, as you can see, right? You're using the same encoding where the same bits RT, these 5 bits over here, refer to either a source register or a destination register. You will see this in LC3 also. So you will need to have the data path elements that take those bits and route it to the right place in the register file so that you can index into the register file. Okay, the most important thing for our purposes right now, because we're discussing literal values, is this literal or immediate. You can express a 16-bit immediate over here. So this is an example, add immediate, and you can see that the opcode is different from add. It's not add anymore, it's add I, add immediate. These are the field values if you want to add 5 to source register 1, S1, which is represented as 16. Sorry. In this case, source register is really the 17 over here, RS, and the destination register is 16. Okay, so basically, you take RS and add to it a sign extended immediate, which is very similar to what we have done for LC3, and store the result in RT. And this is the machine code that corresponds to all of this. This is what is stored in the memory, as you know. Okay, now let's take a look at like why are we looking at this? Because one of the benefits of looking at this immediate is subtraction, right? The question is, do we want to have a subtraction in MIPS in your ISA? In MIPS assembly, you can express a subtraction in different ways. So this is high-level code. Now we have 2 operations, 1 addition and 1 subtraction, as you can see, and you store the result in A. This is one way of doing this in MIPS. Assuming these are in registers, you add the source register 0 to source register 1, put it into a temporary register, and then subtract that from S2, or subtract S2 from that, and put the result in S3. So this is a subtract instruction that looks nice. In LC3, you don't have a subtract instruction. So what you do is this. And this essentially accomplishes the same thing, except the registers are different, of course. But what you do is you add B and C, which are stored in R0 and R1 implicitly. And then you take D, which is stored in R3. You take the 2's complement of it, meaning you negate it. You take the not of R3 and add 1 to it. That's the 2's complement, negative representation. And then add that negative thing to the B plus C that you computed and stored into R2. Okay? So this is the same code implemented in LC3. Yes?
Can you also do in-place operations? So you have the destination register be the same as the source?
You could do that also, yes. That's possible. This is one way these people decide to do it over here, right? Okay, so you can see now immediately a trade-off, right? And this is actually the same trade-off that I was talking about. Do you want complex instructions or simple instructions? Subtract is a complex instruction compared to not and add. Makes sense, right? If your data types can be converted to a negative value using not and add, which almost all data types can be converted, then you can do whatever this is. You can do everything with not and add. You don't need a subtract operation. The benefit of subtract is, of course, now you can see the denser encoding, right? I kind of told you that, but now you can see even with a simple operation like subtract, which is more complex than not and add, you have 2 instructions here as opposed to 4 instructions here. Your encoding is better over here. Okay? Okay, performance is a different thing. You need to optimize the performance of both probably. And I don't know which one would perform better depending on other constraints, right? Maybe you can optimize subtract to be very fast, but maybe you can optimize not and add to be as fast, right? Okay, so you get more instructions in LC3, but control logic is hopefully simpler because you don't have as many instructions, right? Okay, so let's take a look at subtract immediate. So this is our high-level code, B minus 3. Let's play some more games. In MIPS assembly, you can express it this way. Subtract immediate, because you have a subtract instruction, S0, 3, right? But it's really not necessary, because you could actually do it this way also, right, in MIPS. You could do add immediate minus 3, right? Okay, in LC3, essentially you could do the add. In LC3 doesn't have an add immediate. It basically uses the same mnemonic to specify add versus add immediate, and you can distinguish them based on here. But those are all programming constructs also. Okay, any questions? So hopefully that gives you an example of a little bit complex instruction versus simpler instructions. Now, you can generalize this to much more complicated instructions. Okay, now let's talk about data movement instructions. We're going to deal with accessing memory. And we're going to complicate things more because this is going to add more addressing modes. Because how do you address the location of the data that you want to get to? So in LC3, there are actually 7 data movement instructions. We're going to see essentially all of them. We're going to focus more on the loads. And the format of load store instructions look like this, basically. You have an opcode, the top 4 bits. You have either a destination register or source register after that, the next 3 bits. And those are interpreted as destination register if you're loading. Those are interpreted as a source register if you're storing, because storing takes a source register, stores into memory. Loading takes a memory location and stores into a destination register. And then the rest are address generation bits. And how those are interpreted depends on the opcode. And there are 4 ways to interpret these bits. And these are essentially the addressing modes that we have. We've seen some of these. We're going to see more. These are the names of the modes: PC relative, indirect, base plus offset, immediate. And they all have either restrictions or downsides, or upsides, let's see. In MIPS, there are only base plus offset and immediate modes, actually. There's no indirect mode. And there's no PC relative mode, at least for data movement instructions. There's a PC relative mode for jump J-type instructions that we have seen in the past. And we're probably going to see soon again. Okay, let's take a look at this PC relative addressing mode. This is load and store. And we have already seen an example of this, I think. Actually, we have not seen the example of this, sorry. This is the opcode. Opcode can be 0010 or 0011. And they distinguish the load versus store. And if the opcode is that, the next 3 bits are either destination register or source register, depending on whether you're doing a load or store. And this is how you calculate the address. This is actually the semantics, the total semantics of the load. The address calculation is done by taking the PC program counter, which is the address of the instruction, plus actually address of the next instruction, next sequential instruction, because this is the ISA designer specified this as the incremented PC. Take the incremented PC. They had in mind somebody incrementing the PC while you're fetching the instruction. So when you're about to execute the instruction, you have the incremented PC at hand. And you add to it the bottom 9 bits, sign extended. We already learned about sign extension. Essentially, this way, you can go to a memory address that's relative to the instruction. Instruction at this location in memory, you can go up to 155, you can go down to 155. I'm going to give you the exact numbers soon, right? And then take the value in that memory location, put it into the destination register. So this is a limited addressing mode, as you can see. Store does essentially the same thing to calculate the address, but you go to the memory location, get the data value over there, and then put the result into a source register. Okay, we're going to see the limitations soon. So this is we're going to look at the load. This is load. And let's assume that the offset is 1 AF, 9 bits. And this is the machine code that you have. This is how it's executed. Let's take a look at this before we go into the downsides of this. So you basically fetch the instruction in the instruction register. This is the incremented PC. We're going to assume that that's the incremented PC for that instruction. And to execute this instruction, you first calculate the address. You take the incremented PC. We go through a specialized adder for address calculation, which we're going to place in the larger machine later on. You sign extend the bottom 9 bits of the instruction register, add it to the incremented PC. You get the result, which is the address. You place it into the MAR, memory address register. You access memory in a state. Memory becomes ready at some point, and then you move to the next state. When the memory is ready, the data is loaded. Data at this address is loaded into the MDR. And then when you go to the next state, you take the data value in the MDR and place it into the destination register that's specified by these 3 bits in the instruction. So there's some logic that's not shown here, but these 3 bits need to get connected to the index or address decoder of the register file. And you've seen that address decoder when we built memories earlier, right? This is the address. There are only 8 addresses, so you need 3 bits. And you use these 3 bits to decide where to write. And you need to write enable that location because you're actually writing in that state when you're moving data from MDR into the destination register. Again, this is not magic. We've kind of seen it before. I'm going through this again and again so that hopefully it becomes like bread and butter for you. Okay, so clearly there's a restriction to this, even though, I mean, clearly you can do this. But the restriction is the memory address that you can address or specify using this sort of addressing mode is limited. It's very similar to the limitation that we have when we actually use an immediate value to add or subtract, right? You basically have a small number of bits. In the previous case, it was only 5 bits. If you want to add a value that's larger than that you can express in 5 bits, you cannot do that. Here, the memory address is only 255 after this instruction, PC plus 255, and or it's maximum 256 locations before this instruction because the offset is 9. Okay? Yes.
Why don't we use an unsigned integer for memory addresses?
Well, the memory addresses are unsigned. The address is unsigned, but the offset is signed so that you can your relative value. So if your relative value was unsigned, you would only go either forward or backward. You cannot go backward and forward, right? Make sense? Okay. But the address itself has no sign to it because it's really a linear array that grows from 0 to 2 to the n minus 1, where n is 16 in, yeah. Okay. So basically the limitation is the PC relative addressing mode cannot address far away from the instruction. It could be useful because the data may be located close to your program, right? You have your program and your data is before the program or after the program. But if your program is too big, you cannot put the data that close potentially. Okay, that's why people develop other addressing modes. And you could argue that this is not a great addressing mode, and I agree. That's why MIPS doesn't have this addressing mode. This is an instructional addressing mode. Okay, indirect addressing mode. This is actually an interesting one that doesn't exist in MIPS, and it's a more complicated one. And essentially, it's called a load indirect and store indirect, but it could be useful when you're doing pointer chasing, meaning you have a pointer. Pointer is essentially stored in a memory location, but that memory location specifies an address that tells you to go to some other memory location, right? That's a pointer, essentially. Okay, so what does this do? This will become more clear when we do what we're going to do, this instruction specifies. So you can have load and store again. The opcode is like this. If the opcode is like this, the next 3 bits are destination register for load, source register for store. And again, we have a PC offset, 9 bits, but we're going to interpret it differently because of the opcode right now. The difference between this instruction and the previous instruction that we saw is the opcode. And this is how we're going to interpret it. Now, this may look very similar to the previous one, but we have an additional memory over here, as you can see. Memory. What does this mean? We calculate the first address the same way we did the previous instruction. We take the incremented PC, add to it a sign extended 9-bit offset that's coming from the instruction register. We go to that memory location, get the data in that memory location, and we say, oh, this is an address. So I'm going to use that again to access memory. And then get the data from that location. So we first calculate one address, PC plus sign extend offset, go to memory at that location, get the data value. That's our second address. We use that to index memory and get the data value. So you do 2 memory accesses, which means that the first address you calculate is the address of the pointer to the location that you're going to access in memory afterwards. And you could keep doing this. This is indexing using pointers. You could actually do memory, and that would basically enable you to do many indirections through different memory locations to get to what you want, potentially. And this could be very useful if you have linked data structures like graphs, for example, or linked lists, or binary trees. These are constructed using by linking different nodes through pointers in memory. Okay, and store is essentially the same thing. You just store the data by doing essentially the same type of address calculation. Okay, so this is the instruction, and this is an example PC offset over here. This is the machine encoding. Let's take a look at how this is done. We're going to use exactly the same hardware that we designed for the previous instruction, actually. So we have the incremented PC over here. We have the instruction register. We have the sign extension logic for the last 9 bits. The first step is to calculate the first address, which basically takes the incremented PC, adds to it the sign extended 9 bits coming from the instruction register. That's your address. You place it into the MAR. That's the end of one state. And then you go to the second state, which is the memory access state. Memory accesses itself using the value in the MAR, the address in the MAR. And at some point, memory becomes ready and places the result into MDR. Once that's done, you take actually, we're not using the same hardware, as you can see. We're using this connection, which goes through the memory bus, which goes through the bus, actually, processor bus, as we will see later on. But basically, you take the value that is placed by memory into the memory data register. You don't put it into the destination register immediately. You put it into memory address register. Make sense? It happens to be 2110 in this particular example in your book. Okay, so that's the critical step. This is the injection part. You calculate the address, access memory. Memory provided some data. You treat it as an address, and you put it into the MAR. And then we do another memory read. This memory read provides us the data that we're looking for according to the specification of the instruction. And the data, once the memory is ready, you get the data into memory data register, and you place the data into the register file as specified by the destination register bits in the instruction register. Make sense? Clearly, you need to modify the state machine to enable this. So you do 2 memory reads to be able to do this. But now the benefit of this is the address of the operand can be anywhere in the memory. And it's actually more powerful than this because you're actually using some pointer chasing, if you will. Okay, this is an interesting instruction, I think. It's not used in MIPS because it's too complex for MIPS. MIPS, the philosophy of the design of MIPS in the 1980s, actually late 1970s, was let's make the instruction set as simple as possible. So this is too complex for MIPS. And the reason they had that philosophy, as we will talk about when we go into microarchitectures, if you make the machine as simple as possible, the hardware you can design as efficiently as possible. Now, the software job is much harder, of course. And for example, the original MIPS actually didn't even have a multiply instruction. It didn't even have a load byte instruction. They started with load word. Quickly, they figured out, bad idea. People use multiplies all the time. So we cannot just have adds and shifts. They also figured out quickly, loading words is not enough, bad idea. People load bytes all the time. So let's have a load byte. So over time, that ISA becomes more complicated. It's still not that complex as you will implement in your lectures. But this is the idea. That's why they don't have this addressing mode. But they do have this addressing mode, which is equally capable, let's say. meaning I shouldn't say equally capable, but it's expressive enough to address anywhere in memory. Okay, base plus offset, we've seen this. Essentially, LDR and SDR and MIPS do this, and we've already gone through LDR a lot in the last lecture, so I'll go through this relatively quickly. That's this is the encoding, as you can see. And the way address is calculated is you access the base register, which is specified by these 3 bits in the instruction register. You take the value over there, you add to it this sign extended 6-bit offset, and that's your address now. You access memory and get the value in that memory location and place it into the destination register. Makes sense, right? And store is essentially the opposite way. And we've seen this again, but just to show you pictorially, we've not seen exactly this thing over here. Assume that your base register is 2, destination register is 1, and offset is 1D. This is LDR. This is how it executes. You access the base register, which is register 2 in the register file. Actually, this is an LC3, sorry, but MIPS is very similar. So MIPS is going to be very similar, but we're looking at LC3 right now. You can get ISAs confused also, as you can see, because they're very similar to each other in some instructions. But you take the base register, you go through the address calculation adder, that's a specialized adder, and you add to it sign extended 6 bits from the instruction, and that is your address. And that address gets stored in the memory address register. And then you move to the next state in the state machine. That next state does the memory read. And when the memory is ready, the data is placed into the MDR by the memory. And the last state in the execution of LDR is you take the data in the MDR and place it into the destination register, which is 1 in this case. Make sense? Okay. So again, the benefit of this is the address of the operand can be anywhere in memory, but you don't do the injection. So if you do the LDI, you can do 2 of these accesses without going through memory. If you want to actually do LDI using this, you need to do another LDR. Okay, so LDI actually saves 1 more instruction, as you can see, right? If you think about it, if you want to do 2 memory accesses, if you want to access the memory, if you want to treat this thing that you loaded into destination register as another address, you need to do another LDR with an offset of 0 for that. Okay, so let's take a look at the address calculation. Now we're actually making the address calculation more complicated by adding more addressing modes. So this is the global bus. This is the more complicated version, like full version. This is the memory address register multiplexer. So we have a multiplexer over here so that we can put data into the MAR, and we have the data path for that. This is the adder that I was showing you earlier. This is the address calculation adder, which is different from the adder in the ALU. We need to have a specialized adder for this purpose. And these are the sign extension logic that we added. This is the 9 bits coming from the instruction register sign extended for one of the addressing modes, and 6 bits coming from the register for the other addressing mode. And there are other addressing modes that actually we can use that we're not going to look at right now. But essentially, as you keep adding addressing modes, you need to complicate the hardware, which is what I said earlier, right? If you actually have more addressing modes, your hardware becomes more complex. As a result, your design becomes more complex, potentially slower, but you could also optimize it in different ways. Okay. So in MIPS, we've also seen LW earlier. You use essentially the same addressing mode, base plus offset. In MIPS, it's also called base addressing mode. I like base plus offset better because there's an offset actually over there. It's not just a base. So this is the high-level code. This is the MIPS assembly, and we're assuming byte addressable. So you know the reason for the 8s, because assuming this array is an array of words, to get to the second element, second word, you need to multiply the address by 4, because each word is 4 bytes. So this is how you calculate the address. You take the value in register S0, add to it 8, go to memory, and actually this is a store word, sorry. We just decided to use store word. Calculate the location, address of that memory location, and store register 3 into that location. And these are the field values over here. So in this case, because MIPS has larger instructions, the offset, or the immediate value, can be much larger. It can be 16 over here, at a sign extended to 32 bits, of course. Okay, now let's take a look at how these programs work in MIPS and LC3. We're going to look at both stores and loads. These are the MIPS registers that we're going to allocate to. Again, I will not go through this in detail, and you can do it yourself, but what this does is the first load word loads the value into a temporary register A, and then you do an add A plus B, and then add I does the -5. Now T2 stores what we have as C, and you do the store word from T2 to the memory location that's specified by a base register that stores the beginning address of this array. Make sense? Okay, that's hopefully simple. We've gone through all of these instructions. Store word may be slightly new, but it's the same thing as load, except it's the opposite way. LC3 is essentially very similar. So this is the similarity of the ISAs. They have the same addressing modes in this particular case, same types of instructions. And once you have that, it's just a difference of syntax, right? It's kind of like having two different languages, and you use the same type of instructions to implement a particular construct, right? So if your instructions are similar, your ISAs are also very similar in the end, and there's not much trade-off over here. Okay, let's take a look at the immediate addressing mode. This is going to be a little bit different because we're not going to access memory. It may be surprising because we're talking about data movement instructions, but this is really initialization of a register type of instructions. We're going to see the equivalent of this in MIPS. And the idea is load effective address. It should have been called what MIPS called it, in my opinion. It's really loading an immediate value into a register. And you will see the name in immediate. It's load upper immediate, load, yeah, you'll see that soon. But basically, this is what the opcode looks like, 1110, and there's a destination register, and there's a immediate over here specified by PC offset. Actually, this is sorry, it's a little bit different from MIPS because this is really using PC, because you really want to load an address in this particular case. But maybe it's not as general purpose as what we will see in the MIPS. So it's good to think about that. So basically what you do in LEA, in LC3, is you take the incremented PC, you add to it a sign extended PC offset, just like we did in a PC relative mode. As opposed to going to memory, you just load this into the destination register. Does that make sense? You basically load a PC relative address into the destination register without going through memory. So what is the difference? You don't access memory, essentially. Instructions with the PC relative mode that we have seen some number of slides ago load from memory, but LEA does not. So that's the name, that's why it's called the load effective address. If you do this, now you can manipulate things based on the program counter. That's the benefit it provides. But again, MIPS doesn't have this. MIPS actually doesn't provide PC relative addressing for data moment instructions, but you can actually encode this in jump instructions, as we will see again. Okay? Okay, so this is what it does. Even though we cover it in data moment instructions, it's really an odd instruction. It helps data movement because you're loading a PC relative address. You get the incremented PC. You add to it a sign extended 9-bit offset, very similar to a PC relative addressing. It's actually PC relative addressing, but you don't access memory in the end. You take that and place it into the destination register. Now what you have in the destination register is PC plus offset. Make sense? Now you can manipulate something based on the current PC that you have. So it has its benefits. Okay, now we actually complicated this a little bit more. What happens over here is you need to go through, again, the address mux. I will not go through this, but you will study this more and more as the lectures come. Essentially, there's data path that's provided for this as well. So it's really this one. Yeah, there's a PC over here, right? You have the incremented PC that's already stored over here. You select that one and add to it this sign extended 8-bit value, and that's your address. And then you go through the MAR mux over here. You need to set the control signals accordingly, and you put the data value into the register file. Okay, so let's take a look at this. It's a little bit different in MIPS, as I said, because it's not PC relative. And it's arguably, it's because MIPS doesn't allow you to do this PC relative addressing mode, this is a way of initializing the registers. So in MIPS, for example, you have an LUI instruction, load upper immediate, that loads a 16-bit immediate into the upper half of a register and sets the lower half to 0. Slightly different, right? You don't do anything with the program counter. You just take the 16-bit immediate, put it into the upper half. So it's used to assign 32-bit constants to a register. For example, let's say that we have a high-level code that looks like this. We assign a 32-bit value to this variable. MIPS assembly looks like this. So load upper immediate. What it does is it basically, with this instruction, you specify 6D5E, the most significant 16 bits. What this does is it sets the top 16 bits of S0 to this value, okay? And the bottom 16 bits are zeroed out. And then you can OR that value with another immediate that's encoded in the instruction for F3C. Okay, this is one way of initializing values. Hopefully it makes sense. Without going through memory accesses. Another way of initializing value is write some data to some memory location, load it, and then load it into a register. But this way you don't have a memory access, right? You eliminate memory accesses. Okay, it's a very similar addressing mode. It's not exactly the same addressing mode. It's not PC relative, as you can see. But this is very useful for initialization. Okay, this is something that I will not go through. Actually, I'd be interested in giving this to ChatGPT and asking what this program does. These are actually a good way of reverse engineering. But if someone gave you, for example, this entire program, you could reverse engineer it now based on what we have seen. You need a manual, meaning the LC3 manual in this case. But you know what to do. These are the instructions, and you know the opcodes. And you can basically reverse engineer what each of these opcodes do, right? How? You basically take the Pat and Patel book. You start with the back cover, which has this. And then if you don't know exactly how the instructions operate, you need to flip a number of other pages to figure out how the instructions operate. And in the end, you go through the exercise, you figure out these are these instructions, and these are the immediates, and then you figure out the addressing modes, and you figure out exactly what this program does, and you simulate it. And in the end, the final value of R3 is 5. People who do security actually do a lot of this reverse engineering because they don't know what a program does, for example. They're given a bunch of bits, binary zeros and ones, and they figure out what that program does, and then they hack it for a good purpose or for a bad purpose. But this reverse engineering is actually fun. I don't know if you can try it with an LLM and to see if it actually is able to get you the correct value. It's good to check, actually. I'm curious. Maybe one of our TAs will check later on if the students. If you check it, let me know if it gets the right value. But you should be able to do this right now. Based on what we have learned, everything about ISAs today and yesterday, with the right tools, meaning the right manual, you should be able to do this on your own. And it's good to try this. It's actually in your book. Your book already does this for you, but I would suggest doing it yourself so that you see how instructions operate. Okay, let's jump into jump instructions, control flow instructions. So we're going to treat control flow instructions a little bit more, and hopefully we'll be done with control flow instructions by the end of this lecture. These allow a program to execute out of sequence, and we've already discussed this. They could be unconditional jumps, like what we discussed yesterday. Today, we're going to talk about conditional branches. Conditional branches are used to make decisions. For example, you have an if-else statement. If x is greater than 5, do this. Or execute, go to this part of the code. Otherwise, go to this part of the code, right? So in LC3 and MIPS treat this differently. And there are different ISAs that do either what LC3 does and what MIPS does. For example, x86 does similar to LC3. x86 does also other stuff, but condition codes, for example, that LC3 uses are used in x86. Let's take a look at what those are. So jumps, on the other hand, are used to implement loops and function calls. We've already seen jump, JMP in LC3, and J in MIPS. We may see that again. But let's talk about conditional branches, because those enable us to do something more sophisticated. Based on a condition, you jump to a particular part of the program, or you go in sequence. That's the idea. So how is this supported in LC3? So in LC3, each time you write a general purpose register, there are 3 single-bit registers that are updated. So while you're writing to the general purpose register, there's also something else happening in the data path that says, check the value that I'm writing and set the condition codes. Each of these condition codes are either set to 1, or cleared, set to 0. So if the value that I'm writing to the destination register is negative, you set the n bit. and Z and P are cleared. Now that means the value is negative. Clearly, it's not 0, it's not positive. If the written value is 0, you set the Z bit. If the written value is positive, you set the P bit. So clearly now you get the idea, right? You have NZP, and this specifies whether the last value that you wrote to a destination register was negative, 0, or positive. Clearly, only one of those could be true, right? A value that you write is either negative or 0 or positive, and you don't get any of those other combinations. So none of those, only one value should be 1, and exactly one value should be 1. So x86 and Spark are actually examples of ISAs that use condition code. This is used in real life. If you program in x86, you will see it. So let's take a look at branch if 0. So this is the assembly of this. This is the encoding. So the branch opcode happens to be 0000. There are 3 bits in the instruction encoding, which tell you which condition code does this instruction test. In this case, branch if 0 means that you should change the program counter to a target value only if the condition code is 0. The small NZP are the instruction bits to identify the condition codes to be tested. And these are the registers that are set by when you write to a destination register, large NZP. Those are the values of the corresponding condition codes, in other words. PC offset is the usual PC offset that we're used to, immediate or constant value, 9 bits. And this is the semantics of the instruction. If I'm testing for the N condition code and the N bit is set, or if I'm testing for the P condition code and P bit is set, or if I'm testing the Z condition code and Z bit is set, meaning the value that was written was 0, then I change the program counter to incremented program counter plus sign extended PC offset. Otherwise, I don't do anything, meaning PC was incremented anyway, so I go to the next instruction. So I branch only if I'm testing a condition code and that condition code is set. That's a more human way of describing it. Branch 0 means I'm testing the condition code 0. If the last value written was 0, then I'm going to take that branch, meaning I'm going to change the PC to PC plus sign extended offset. Hopefully that makes sense, right? Okay, this may be a little bit mystical, but it's really, you just test the condition code, and if the value is negative, you take the branch, otherwise you go to the next instruction. Okay? All right, so let's take a look at how this is executed. This is how it's implemented in hardware. Now we have condition registers, NZP. These are actually special purpose registers. Remember, we talked about general purpose registers. That's the register file. Now we have special purpose registers. Each of them is 1 bit. They're called condition codes. NZP, and I already described how they're set. The last value that you wrote to a destination register can be negative, 0, or positive. I'm not showing the logic that sets these condition codes here. There should be logic that sets the condition codes. When you're writing it to a destination register, there should be a comparator that compares that value to 0, for example. Actually, yeah, there should be a 0 comparator, unfortunately. And you know how to design this. You could design it. That's the hardest part. Negative and positive are maybe easier, but you need still a 0 comparator. Anyway, so basically how this instruction is executed. You have the opcode, it's a branch. Z bit is set, so you're testing the Z bit. So you have an AND with the Z bit. This yes means whether the branch is taken or not, right? Whether you're going to change the PC to PC plus offset. Okay, so there's actually a multiplex, actually a write enable signal or a multiplexer depending on how you implement it. If this evaluates to yes, then you take the incremented PC, add it to it. Concurrently, there's an addition going on. The incremented PC comes here to one input of the adder. This is a special adder also that adds, that generates what the next PC should be. Sign extended 9-bit immediate over here. And then you basically decide whether you write this into the program counter. So if this yes is true, you write enable the program counter. Again, it depends on the implementation. That's why I don't want to go into the implementation exactly over here, but you will see an implementation later when we discuss things. You set the program counter to the target value only if the condition code you're testing is true, meaning 1. Makes sense, right? And you can guess this logic. Now there are interesting things you can play. What if you're testing all of the condition codes? N is 1, Z is 1, P is 1. This is called branch NZP. then what do you do? Yes.
Well, if n, so the capital N, Z, and P must always, there always must be one, it is one.
Yes.
It is always one.
Exactly. Basically, you always take the branch. Now, if this is the branch that you encoded, this is an unconditional branch at this point. Even though you're testing all the condition codes, you should take the branch. Now, there's another game you can play. What is N, Z, P are all 0. If you're not testing any of these bits, yes? Yeah, it's a no-op, basically, no operation, meaning you always go to the next instruction. This branch is doing nothing, right? It's a way of implementing a no operation. And there's a reason we use no-ops, as we will see later in later lectures. Okay, MIPS does it differently. There's a branch equal. Now, MIPS is more complicated here. What it does is basically, this is the branch opcode. Source and there are two source registers, RS and RT. And this is the specification of the instruction. And there's an offset. If MIPS checks if the data value in RS is equal to RT, if that's the case, if these two data values are equal, then the program counter is changed to PC plus sign extend offset. That's left shifted because of byte addressability. Otherwise, you don't take the branch. It's called branch if equal, essentially. You test two registers. And there are other variations of this. Branch if not equal, branch less than or equal to 0, branch greater than equal to 0, etc. There are other variations of this. But branch equal is useful for implementing branches. So let's take a look at how to implement this in MIPS. So the same instruction, this instruction is implemented with 4 instructions in LC3. That's the benefit of branch equal. So you're checking two registers. If two registers are equal, so a loop condition, for example. If one register is the counter of the loop, how many times you iterate on the loop, and the other register is how many times you should iterate to execute the loop. Once you get to the number of iterations you should iterate, you should take the branch, meaning get out of the loop, right? That's the benefit of BEQ instruction. If you want to implement this in LC3, you don't have a BEQ, you just have condition codes. So what you do is you take one of the registers, R1, take 2's complement of it, and subtract it from the other register that you're comparing to R0 in this particular case. And if the result is 0, then you take the branch. So this add will set the condition code. And if the result is 0, that means R0 minus R1 is 0, meaning R0 and R1 are equal to each other. And then you take the branch. Now you see another trade-off in the instruction set, which is essentially a very similar trade-off that we have seen. The same functionality, exactly the same functionality requires 4 instructions in LC3 and only 1 instruction in MIPS. But the control logic requires more complexity in MIPS right now because you need to take 2 registers and compare them and then branch based on the value. So this is the same trade-off that we have seen earlier, which is where do you put the instructions? Are they more complex? Are they more simple? I didn't give you extremely complex instructions, clearly. But even with very simple instructions like BEQ, there is a level of complexity involved that's more complex than primitive instructions like not, add, and branch with condition codes. Okay, so we were able to cover actually all of what I really wanted to cover. We covered a lot of things today and yesterday. There is a lot more to cover on ISAs that we're not going to cover. If you're really interested, there are a lot of trade-offs over here that we're not going to go into. There have been many different ISAs over decades. So later, for example, we're going to look at some GPU type of ISAs. We're going to talk about VLIW. It's too early to talk about these, but these are some names that I'm throwing at you. All kinds of ISAs are there, and the fundamental differences are essentially in, at least from an instruction set perspective. There are other differences from a system level perspective that we may get into. How instructions are specified and what they do. How complex are the instructions, data types, and addressing modes? For example, VAX was a very complex ISA. It had many instructions, maybe more than x86 today. x86 over time evolved over the course of 50, 60 years, and it added many, many instructions. So it's pretty complex. Some of the ISAs are much simpler, actually. Okay, I think this is a good place to stop. Maybe, let's see. No, I'm right on time. This is just a good place to stop to remind you the semantic gap. This is where the ISAs differ. Next week, we're going to cover a little bit more on the ISAs, and then we're going to start the microarchitecture, which is really the implementation of the ISA. So have a good weekend. I'll see you all next week.